Mathematics, Dr. SNS Rajarashmi College of Arts and Science. Today's topic is Graphical Solution Method in LPP. Linear programming is a mathematical technique used to optimize a linear objective function subject to a set of linear constraints. The graphical method is one of the simplest and most initiative approaches to solving LP problems, especially when there are only two decision variables. This method involves representing the constraints and the objective function graphically on a two-dimensional plane by plotting the feasible region defined by the constraints and identifying the optimal value of the objective function at the vertices, that is corner points of this region. The graphical method helps in finding the most efficient in solution. Though limited to problems with two variables, this method provides a visual understanding of the concepts of feasibility, boundedness, and optimality in a linear programming problem. Graphical solution of LP models. If the objective function Z is a function of two variables, then the problem can be solved by graphical method. More than two variables, we can use the other methods like a simplex method. Okay, the procedure is as follows. Step 1. First of all, we consider the constraints as equalities or equations. Step 2. When we draw the lines in the plane corresponding to each equation obtained in step 1 and non-negativity restrictions. Step 3. Then we find the permissible region, that is region which is common to all the equations for the values of the variables, which is the region bounded by the lines drawn in step 2. Step 4. Finally, we find a point in the permissible region which gives the optimum value of the objective function. Step 5. Next note. If there is no permissible region in a problem, then we say that the problem has no solution using graphical method. Next one, if the maximum value of Z appears only at infinity, then the problem has unbounded solution. Last one, if the maximum value Z appears at 2 points, there exists infinite number of solutions to the LPP. Next, problems on graphical solution of LPP. Problem number 1. Solve graphically the given LPP. Problem is maximize Z. Z is equal to 40x1 plus 50x2 subject to the constraints x1 plus 2x2 less than or equal to 40. Second constraint 4x1 plus 3x2 less than or equal to 120. Third non-negativity restriction are given x1 x2 greater than or equal to 0. Solution. Considering the first step, considering the constraint inequality as equality. So we take as the inequality constraint x1 plus 2x2 less than or equal to 40. Let us take x1 plus 2x2 is equal to 40. Then second constraint is 4x1 plus 3x2 less than or equal to 120. We take as a 4x1 plus 3x2 is equal to 120. Now we have to find the points of the lines. The first line is x1 plus 2x2 is equal to 40. If we substitute x1 is equal to 0, then we get x2 is equal to 20. Therefore, the point is 0, 20. And we substitute x2 as a 0, then x1 is equal to 40. Therefore, the point is 40, 0. Therefore, the first constraint points are 0, 20 and 40, 0. The second constraint 4x1 plus 3x2 less than or equal to 120, we take it as 4x1 plus 3x2 is equal to 120. First we put x1 as 0, therefore 3x2 is equal to 120, therefore x2 is equal to 40. The point is 0, 40. Then the second we put x2 as a 0, therefore 4x1 is equal to 120, then x1 is equal to 30, therefore the point is 30, 0. The constraint 2, the equation 2, the points are 0, 40 and 30, 0. This is the graph for this lines, first line, second line, and the two lines connecting points as a feasible region points. This is next we take as the feasible points, that is we pointed as A, B, C, D. Then A is the point 0, 0 as origin. Then B is a point 30, 0, and C is a point 24,8, D is a point 0,20. Now we have to find Z is equal to 40x1 plus 50x2. We substitute A point 0,0, then we get Z is equal to 0. Then we substitute the point B 30,0, then Z is equal to 40 into 30 plus 50 into 0. Therefore the answer is 1200. The point C is equal to 24,8. Therefore 40 into 24 plus 50 into 8, we get 1360. The last point D 0,20, 40 into 0 plus 50 into 20, we get 1000. Here our objective is maximize the problem. The answer is the maximum value is here 1360. Therefore the maximum Z is equal to 1360. X1 is equal to 24 and X2 is equal to 8. Next we have to have the second problem. Solve graphically the given linear programming problem. This is the problem. Objective is minimize Z is equal to 3x1 plus 5x2, subject to minus 3x1 plus 4x2 less than or equal to 12, x1 less than or equal to 4, 2x1 minus x2 greater than or equal to minus 2, x2 greater than or equal to 2, 2x1 plus 3x2 greater than or equal to 2, and x1, x2 greater than or equal to 0. Here 5 constraints are given. Solution. Considering the points, considering the inequalities as equalities. First constraint, minus 3x1 plus 4x2 less than or equal to 12. The equation is minus 3x1. Let us consider the equation 3x1 plus 4x2 is equal to 12. The points are 0,3 and minus 4,0. The second constraint is given x1 less than or equal to 4. Therefore x1 is equal to 4, which is a vertical line passing through the point 4,0. x1 value is not changeable. Therefore we change x to 0, 1 like to this. Therefore the vertical line is given 4,0, 4,1, 4,2 like that. The third constraint is 2x1 minus x2 greater than or equal to minus 2. We take it as a equation 2x1 minus x2 is equal to minus 2. The points are 0,2 and minus 1,0. Next constraint, x2 greater than or equal to 2. Here x2 is equal to 2. Therefore x2 is no change in that line. x2 is equal to, we take it as a x1 as 0, 1, 2. Therefore we get a horizontal line passing through the point 0,2. Next the constraint 2x1 plus 3x2 greater than or equal to 2. That implies 2x1 plus 3x2 is equal to 12. That the points are 0,4 and 6,0. This is the graph. This is the graph for this points. The shaded region, pink color is the feasible region. We get the points, 4 points connecting A, B, C, D. The points are given the next table. From the graph, the feasible region is 5 points are given, A, B, C, D, E. The point A is equal to 3,2, B is equal to 4,2, C is equal to 4,5, 18,5, D is 4,6, E is 3 by 4, 7 by 2. Now we have to find the Z value. 3 into x1 plus 5 into x2. The first, we substitute the first point A. 3 into x1 is 3. 3 into 3 plus 5 into 2, we get 19. Second, the point B, 4,2. 3 into 4 plus 5 into 2, we get 22. Next, the point C is 3 into 4 by 5 plus 5 into 18 by 5, we get 102 by 5. 3 into 4 plus 6 into 5, we get 42. Then the point E is 3 into 3 by 4, 5 into 7 by 2, totally we get 17 by 4. Here our objective is minimize the problem. Therefore minimum value is here 19. Therefore minimize that is equal to 19. The corresponding optimum values of x1 is equal to 3 and x2 is equal to 2. Thank you.